All right, ladies and gentlemen, you don't even know it, but you are in for, oh my gosh. I mean, this is something huge, huge. So huge, in fact, that I'm going to tell you that it's probably not going to appear on the AP test, at least the beginning portions of this. But what this is going to do, because you're probably saying, well, Mrs. Seagrave, if it's not going to appear on the AP test, why the heck are we learning it? Because what it's going to do is offer you a better understanding of how bonding actually works. This is stuff that actually used to be on the AP Chem test, and they've revised and revamped and changed a little bit. So there are sections of this that you'll never see on the test, and I'll be sure to point those out. There are sections that appear on the test that are of lower they're doing it less than they did before. And then the very end of this, in which you will see special appearances by bond length, bond strength, and bond order. Yeah, that's on the test. So just understand as we get started with this video that part of this is for your own better understanding of bonding. Part of this is definitely on the test, and I will indicate when and where each of these things appear. So you're going to get a little bit of like super duper extra. So moving on, we're going to talk here about hybridization, valence bond theory, and again, bond length, strength, and order. Here we go. Okay, so what you have typically worked with is what's called localized electron model. It's called valence bond theory, which are, again, just two ways to say the same thing. You know what this is, not by name, but because this is all you've learned. What we've learned so far is that we have, in terms of covalent bonding, that there are two shared electrons between two atoms, right? That they're kind of localized. And the localized electron model, as it says in the last bullet point here, it tends to prove predicted VSEPR geometry. So basically, this is exactly what you've been using up to this point. We've been talking about how there's two electrons, they're shared, and because they're shared in this way, this is how the geometry would work. So you've been doing this. However, as it says in that second bullet point in the middle, it does go beyond just what you've learned. So that's where we're going to just take one extra step kind of into infinity and beyond, and we'll see if we can make a little extra sense out of this. So the basic theory as far as valence bond theory goes has two big points. Point one, an orbital on one atom comes to occupy a portion of the same region of space as an orbital on another atom. Simply put, orbitals overlap. So this is something that I think you know already. When we did our initial video on how to draw Lewis structures, I created Venn diagrams around the atoms to determine if they were happy or not, and that is essentially showing orbital overlap because those two circles that I drew did overlap. So again, you really do know number one, we've just never specifically stated it. Number two is going to be maybe a little bit extra. So the two orbitals then share no more than two electrons. Okay, continuing on. As orbitals overlap, the electrons start to move around both atoms, which pulls the two atoms together. Now, this is where it's a little extra because we like to think of covalent bonding as these two electrons being held perfectly smack dab in the center, or maybe a little closer to one atom or another, but not zooming around one atom and then zooming around another atom. This is similar to, if you can picture it in your head, imagine Earth and Mars are right next to each other, very, very close. And our moon orbits us, and then it goes and it orbits Mars, and then it comes back and it orbits us again, almost doing a figure eight around our two planets. If the moon is considered to be electrons, and that is what's bonding us and Mars together, then that's a description of what we're talking about right now, is that these electrons actually do move around both atoms, and that is what acts to pull them together. The greater the orbital overlap, the stronger the bond. Okay, that should make a little bit of sense. The greater the overlap, the stronger the bond. This is like a people relationship type of person. Like the longer you've known someone, the more your lives begin to overlap and the stronger your bond with that person. So it's really, really similar. And in order to form a strong bond, Orbital overlap must occur in the direction in which the orbitals point. And that might be where I lose you just a little bit, and I'll show you pictures coming up later, so hold that thought. But basically, we've talked about electron clouds and how an s orbital it tends to be a circle shape, and how the p orbital tends to be a dumbbell shape. So if you think about especially the dumbbell shape of the p orbital, and then notice the wording here, in the direction in which the orbitals point. Well, you can have a dumbbell shape and have it pointing in one direction or another, and it's very clear that it's not pointing in the opposite direction. So again, we'll get to a little bit more as we continue on. So the basic theory is that I think most of this is pretty easy to understand, but there is an advanced portion. So this is kind of what you've already known a little bit about. Now advanced. So as it says, this is information that is way beyond the required AP curriculum. I think it's useful because it does, as it says in blue, deepen your understanding of bonding. And this is something that I think, if you're going to deepen your understanding of anything, bonding might be a good thing. So follow along. Atoms tend to form the number of bonds equal to their number of unpaired electrons. Okay, what the heck does that mean? Well, how about an example? For the example of nitrogen, you can see that I have the electron configuration here, 1s2, 2s2, 3p3. Notice it's got 3 unpaired electrons. If you think about drawing an orbital diagram with the lines and then the arrow up, arrow up, arrow up, again, 3 unpaired electrons. And nitrogen, by the way, tends to form basically 3 bonds. Li3N would be a common compound that lithium and nitrogen could make, and you can see the 3 lithiums attaching to the 1 nitrogen. That's 3 bonds for the nitrogen. Okay, so for carbon, do you notice that carbon here, based on its electron configuration, 1s2, 2s2, 3p2, so 2 unpaired electrons, 2 bonds. Well, hold on 1 second, because carbon can form 2 bonds, carbon dioxide, for instance, but actually what's way more common is CH4. That's 4 bonds. That doesn't make any sense. What the heck is going on? So this is where we actually take it into that advanced study. Why? How? What in the world is going on? Well, here's what happens. Atoms, like carbon, for instance, they undergo something called hybridization in order to achieve maximum stability. Chemistry favors stability, and also maximum number of bonds. So when you think about the word hybrid, I'm sorry, I always go to vampire and werewolf movies. Inevitably, in one of those movies, there will be a vampire fall in love with a werewolf, and they have a baby. And the baby now has some hybrid qualities, and it's both, but stronger and better and everything else. So when you talk about hybridization, in terms of chemistry, it's really the same thing. You're taking 2 things that are kind of distinctly different, and you're kind of meshing them together. And what we're going to find that we're meshing together is orbitals, s orbitals and p orbitals. We're sort of meshing them together. And so instead of having a sphere and a dumbbell shape, we're going to have something that looks a little bit in between. So we'll continue on with that and see what sense we can make of that. So continuing on with our advanced theory, if we take a look at the electron configuration for carbon here, again, instead of using lines, I have my arrows and boxes here, so hopefully that doesn't mess you up. But you can see a full 1s, a full 2s, and then you can see those 2 unpaired electrons in the p. So as written, as we've already discussed, 2 unpaired electrons, it means that carbon really should only be able to form 2 bonds because the other electrons are wrapped up and full in their energy levels, and that makes them happy. But what really happens is carbon does something that's called promotion. Carbon promotes one of its 2s electrons. So again, here you see that there's 2 electrons here. When you look at my next picture, you can see now there's only 1. So it promotes it into the empty 2p space. So one of these is going to pop way up here, and you can see that happened here. So this is empty now, and now that's full. And now, do you see 4 unpaired electrons? Whoa. I just blew your mind, didn't I? Yeah. Crazy, huh? I mean, it's like juggling. I've got I got a bunch of candy bars, and instead of holding 2 in one hand, yeah, that doesn't work because I don't have 3 hands. It's like juggling. Let's just go with that. Okay, so we have this opportunity where carbon can promote. And if you continue on, what this means, this second picture here, the second diagram, what it means is that carbon has undergone, again, what's called hybridization. All of these orbitals, and this is maybe the weird part, because when you look at that previous picture, you see one S electron, and now you have three P electrons. But read with me, all of the bonding orbitals are considered equivalent now after hybridization has been completed. You're kind of meshing together, and now you're considering that they're all the same. But by the way, they're not S's and they're not P's. So for carbon, the bonding of the four different atoms, with four different atoms can occur in one S as well as three P orbitals. Each bond is now called something different. So it's not an S and it's not a P, it's something in between, and it's called an sp3 hybrid orbital. Instead of distinguishing, as I say here, between plain old S and plain old P, we're kind of meshing it. Now notice the count. Do you see how there's one S, and apparently with the superscript of a 3, what I'm saying there is that there are 3 P's. So there's one S and 3 P's for a total of 4 orbitals that are being occupied by lone electrons. And that's kind of where it comes from. So it's named sp3 because one S, 3 P's were hybridized together. And you can see again in the drawing, by what I have in the blue circle, this is now all that's in the blue circle is considered the sp3 hybrid orbital. You following? So again, this is where bonding would now occur because these are now considered all valence electrons. It does also help maybe to note that these are all second energy level electrons. So 4 valence electrons and 4 bonds possible. So again, it sort of makes sense with things that we've talked about before. Looking at the periodic table, it's pretty obvious that it's in the 4th group across, and that's 4 valence electrons. But when you look a little closer, you recognize that 2 of those are actually paired and 2 are unpaired, and bonding can only occur with unpaired electrons. So this idea of hybridization to move one electron out creates now 4 unpaired electrons for 4 bonds, and now it's a hybrid, an sp3 hybrid. Okay, so questions, definitely make sure you jot them down, and we're going to go on to then determining what is the hybridization of a molecule, because this is the way that you could see it now on the test. So understanding some of this advanced theory is actually not a necessity. What is a necessity is understanding that if you see the letters sp3 together, that's talking about a hybrid orbital, and that if they gave you a molecule and said, what's the hybridization, you would be able to come up with an answer. So that's what I'm going to do next. So next, important, okay? Steps to follow to determine hybridization of any atom you'd ever run across. Okay, first thing you're going to have to do, because this is all related back to molecular geometry also. So first thing you're going to have to do, you better draw a Lewis structure. Second thing you're going to have to do, you better make sure that you know the molecular geometry. It's, again, as it says in parentheses, it's not a requirement to determine hybridization, but it's good practice, and it's a good thing to have in your mind a 3-dimensional vision of what the molecule looks like. So definitely got to draw the Lewis structure. After that, then you will count the bonds and the electron pairs around the central atom. Electron pairs, single bonds, double bonds, and triple bonds. They all count as 1. Each one, you just count 1. And then as you count, you're sort of, instead of going like 1, 2, 3, 4, or A, B, C, D, what you're doing is you're counting with sort of a funky little numbering system, and it would go like this: S, P, P2, P3, D, D2. And you'd never go any higher than that. And in fact, on the test, they'll never go into the D's. So really all you have to memorize is SP, P2, P3, or as I say it, SP2, 3. Kind of rhymes. It's kind of nifty. So these are the steps. You want to make sure that you understand these steps. However, understanding them fully really comes into play when we do it. So that's what we're going to do on the next slide. And here we go. All right. So in the different pictures here, the different white boxes, you can see you have different molecules set up here. We have PCl5, which would be phosphorus pentachloride. We have SEF6, selenium hexafluoride. We've got I3, these are I's, So 3 capital I's, we have iodine. And then finally, we have C2H2, which is called, as it pops up right here, acetylene. So my question for you is, what is the hybridization of the central atom of each of these molecules? So I'll do the first one with you, and then I'll ask you to try the next ones yourself. Okay, so again, every bond, whether it's single, double, triple, and every electron pair, everything counts as one, and all you gotta do is count. So follow along with me here on our phosphorus pentachloride, and here's how we do it. So I'm gonna start there, and that's simply because I want to. You can start any place you want. And I'm gonna start counting, and I'm gonna say S, P, P2, P3, and I got one left, and that would be a D. So you count around, so basically you've counted 5, but S, P, 2, 3, D, and that final thing that you get then tells you what your hybridization is. So the overall hybridization is here in blue. Phosphorus pentachloride is considered an sp3d hybrid. What that means is that there would be a lone electron in the S, there would be 3 lone electrons in the P, and then there would be a lone electron in the D. So you have now hybridized, you've actually promoted electrons to create 5 orbitals that have lone electrons, and those are the ones that become hybridized and kind of a mishmash of the S, the P, and the D shapes. So just a really crazy shape for the molecule. So sp3d hybrid. Again, all you've got to do is count. And on an AP test, they will not anymore go into the Ds. So the highest you really need to know is sp3. Okay, so continuing on, let me do selenium hexafluoride with you real quick. So again, starting wherever you want, S, P, P2, P3, D, and D2. And by the way, that's the highest we could ever go because that's an octahedral geometry and that's as big as it gets. So that is considered an sp3d2 hybrid. Okay, see if you can please try the next 2. Remember, single bonds, double bonds, triple bonds, and electron pairs all count as 1. Pause the video and try them, please. Okay, so my hope is that you were able to understand that you count everything. So there's an S, there's a P. That's a P2, that's a P3, and there's a D. And so overall, this would be sp3d. Everything counts. As you look at the acetylene next door, S, P. Now notice in this case that there are 2 carbon atoms and they are sharing central atom duties. So sp, that's where you stop. You don't continue counting any further because you're just looking at 1 carbon. So you can do this for each carbon within a very big structure because you consider the carbon the center and then you just look at the bonds that are attached to the carbon. So this one, this very last one here that we just did, this is the type of thing you could definitely see on an AP test because it doesn't go into the D. It's asking you to recognize that you understand that a single and a triple bond are counted exactly the same, and this is again an sp hybrid orbital, or the hybridization of acetylene is sp, to put it a different way. Okay, so some examples are helpful, I think, but I also do want to show you some pictures, which are pretty cool. So moving on, descriptions of multiple bonding. Another way to describe this, besides having our electron configurations with, the boxes and the arrows and everything like that, is to talk about shapes. And I've been kind of alluding to the idea of shapes. We're really only going to talk about shapes in terms of S and P, but you do need to know something on this sheet right here, and it's the second bullet point. It's the idea of a sigma and a pi bond, okay? Depending on shapes and how they connect to each other, and we're talking about shapes of orbitals, that is, they get a sigma or a pi designation. So something is called a sigma bond, and you can see the little sigma abbreviation here, like an O with a floopy on it. And then you could have a pi bond, which uses actual pi for real pi. So what we will be understanding as we continue on here is what's a sigma bond and what's a pi bond. And they will ask you on the AP test, here's a chemical, here's its structure, how many sigma bonds, how many pi bonds. Okay, so you need to know this. So this is all going to be kind of based on, again, those shapes. So we've talked about this already in this presentation. S orbitals have sphere shapes and P orbitals have dumbbell shapes. So you can see my 2 shapes right there. Okay, continuing on. So the sigma bond, this is definitely what you want to understand. So really, really important here. The sigma bond is a bond formed along an axis, meaning that it's in a straight line. A sigma bond has a cylindrical shape, and a sigma bond can be formed in one of two ways. You can have two s orbitals overlap. Now think about it. If you have two spheres, is there any way to overlap them that they would not be along an axis and have a cylindrical shape? No, not really. So two s orbitals overlapping, that's automatically a sigma bond. If you have an s and a p orbital overlapping, they would have to bond in the plane. So again, think of a sphere, the S, and then think of that dumbbell shape. Well, I have to put the dumbbell shape horizontal in order to match with the sphere shape to create that cylindrical shape. If I take the p orbital and flip it on its head, it's going to be going up and down, and the S is just a sphere, and that doesn't create a cylinder shape. It creates almost like a T shape. So as long as I have the P oriented in the right direction, I can create a sigma bond from that, and it's bonding along an axis. And then the final option is an s orbital and a hybrid orbital. So again, it could be like an sp orbital or an sp3 orbital or something like that. So let me give you some pictures, because I think the pictures help a lot too. So these, I apologize, these should be full perfect cylinders in there, or I'm sorry, spheres, and they're not. But these are two S, supposed to be spheres, and you can see how they overlap, and that's along an axis, and it has a relative cylindrical shape right in here. Okay, this is again that side to side S and a P. So the S is the darker yellow, the P is the lighter yellow that has the dumbbell shape. And then this is what a hybrid would look like. So remember I said with the hybrid, you're taking features of both and you're kind of melding them together. So in this hybrid orbital here, made of these two lobes, you can sort of see a large sort of normal P shape dumbbell part, and then sort of a shrunken section. And that would be the effect of the S sphere on the overall shape. So any of these would be considered sigma bonds. Okay, so hold that thought for a second, and let's talk pi bonds. So sigma bonds. They are, actually, sorry, before we go on, the first bond formed is always a sigma bond, and that's going to be important to understand when you're talking about multiple bonding. So if we do a single bond, well, that's the first bond formed, right? That's the only bond formed, and that's a sigma bond. So any single bond is always a sigma bond. Now, if I go on and I create a double bond or a triple bond, please understand that each of those bonds happens in succession. So you would have the single bond created, the first bond, it's a single bond. Well, what about the next bond? And if I'm going to create a triple bond, what about the next bond? Those other two bonds are not sigma bonds. In fact, they are, as you may be able to predict, they're pi bonds. So the pi bond is a bond formed above and below the bond axis. So making a sigma bond, you form the axis. And then when you do a pi bond, you form it above and below. And it basically will always be sideways. It's like, imagine two parallel p orbitals, those dumbbell shapes, sideways overlapping. So the top dumbbell and the bottom dumbbell are lined up right next to each other. And it is not as strong as compared to the sigma bond. The sigma bond, being along an axis, is sort of like direct pull. Whereas when you go above and below, it's just a little bit weaker. And in part, that's because of rotation, which I'll talk about in just a little bit. So as I said on the last slide, sigma bonds always form first, and then the pi bond can form. So that sigma bond will form along the axis. It'll really hold the structure together, and then the pi bond can actually form after that. So in order to show you a pi bond, we have to actually take a look at the structure of something that has a double bond, because again, the first bond would be a sigma, and the second one would have to be a pi bond. So watch with me, okay? This is going to get really messy really fast. Okay, so I have blue orbitals here, spherical orbitals around my H's, because that's all H has. That's all hydrogen has is an s orbital, so it's a sphere. So there's my hydrogen atoms kind of sticking out there. And I'm also going to put now my bonds together. So the red orbitals that I've just put around the carbons are sp2 hybrids. And by the way, check it out, sp2, right? sp2. sp2 hybrid. So that's an sp2 hybrid orbital. And I have to bond the carbon and the hydrogen together with some sort of overlap. So do you see that it's like head-on overlap? It forms an axis, and those would be sigma bonds. But I also have to bond the carbons together. And these, by the way, are also, they're like the other side of the hybrid orbital. So if you remember the previous picture a slide ago, I showed you that S plus the hybrid, and it had kind of a dumbbell shape and then sort of a smaller shrunken shape. And that's what I'm showing you here. So it's the smaller shrunken shape that holds the carbons together. But again, do you notice this is really head-on overlap, and it forms a bond axis of cylindrical shape if you think in 3 dimensions. Okay? Now, that's not all, because if you actually recognize what the overall electron configuration looks like, there are actually going to be, in this case, 2 unhybridized orbitals for carbon. And those are going to form the pi bond. So as you see now, these green dumbbells are going up and down. And what's going to happen is I have these yellow lines that I popped on here. That's attraction. So there's going to be attraction both above and below the bond axis. And what that does is it actually locks that structure in place. If these bonds, let me take them away a second. If those bonds are not there, right in here, there can be rotation. And so this side and this side can actually rotate in opposite directions from each other if they wanted to, because this is a cylindrical shape and it's along the bond axis and the whole thing can rotate. But if I bond with a pi bond and I put in those yellow marks, what that's saying is that that now cannot rotate any longer because it's sort of locked into place. Okay, so every bond that is between a carbon and a hydrogen is a sigma bond, because again, that's the first bond that forms. So you have 1 sigma bond here, 1 sigma bond, 1 sigma bond, and 1 sigma bond. So that's 4 sigma bonds so far. And then the carbon-carbon double bond, the first bond, remember, is a sigma bond. So that brings our grand total to 5 sigma bonds. And then you can see the green overlapping here, that would be 1 pi bond. Now understand, you're not going to have to draw anything like what I've drawn in all this color. What you need to understand is if they show you this structure, you have to be able to tell them that there are 5 sigma bonds and 1 pi bond. Okay, so do you think you can do that? Every bond that's a single bond is sigma. And then when you have a double bond, the first one's sigma and the second one's pi. Okay, so this is our double bonding section. And as I already mentioned about rotation, rotation is possible around the carbon-carbon double bond, even with this, okay? Because imagine that these little yellow lines could actually break for a moment, and you could have quick rotation, and then they could form again. So, and we also set up here, not as strong of a bond as compared to the sigma bond. So these little dotted lines are meant to show a weak attraction, so that can break and reform, so it can lock it into place and then it can be free to rotate. Lock it into place, free to rotate. And as we go on to the triple bond on the next slide, you'll see that rotation is not as possible at this point. Okay, so here's a triple bond. This is C2H2. This is acetylene with your triple bond in the middle. And we're going to basically go through and do the same thing. So we need to put shapes around our H's to show that we have an orbital. And then we need to bond the carbons to the hydrogen. So there's our sp hybrid orbitals for carbon. We now need to bond the 2 carbons together in the middle. And we're going to do that first with that hybrid orbital, and it will be head-on sigma. Now keep track. Okay, we got 2 more bonds left, right? So the first one's sigma, the second one is pi, and the third one is also a pi bond. So that means we're going to have unhybridized p orbitals kind of overlapping up and above and beyond, I'm sorry, not above and beyond, above and below the bond axis. So I put them on an angle here because I want you to see that there would be these 2 that could kind of bond together, and you can see the yellow lines to indicate attraction. But then I have to fit in another one there, and I'm going to put it in a separate direction because it can't all overlap in the same way. And then I have some purple lines to show attraction there. So now what you've got is you have sigma bonds. So you have a sigma bond here between carbon and hydrogen, a second one here, and a third one in the middle. So there's 3 sigma bonds. And we, in fact, then have 2 pi bonds, which would be the equivalent of like the double bond and then the final triple bond between the carbons. And then notice what I have here at the bottom. These pi bonds will lock a structure into place, because in order for rotation to happen, I have to break the yellow connections and I have to break the purple connections. Well, what's the chance that I'm going to break all of those at the exact same time? Slim to none. The chances are very good that I might break the yellow, but the purple would still be in place, or vice versa. And I can't rotate that around in any way unless I break everything at the same time. So when you have triple bonds, there's very little rotation within the structure. Double bonds do have the opportunity for rotation because you just have to break some weak connections once. Rotation can happen, and then it can actually rebond and reform. Okay, so that's definitely, it's been a long video so far, I recognize. There's a little bit more to go as we talk about bond length, strength, and order, which is actually going to go a lot faster. But please remember that what we've covered so far, you have to know hybridizations. You have to know the SP, SP2, and all that. I want you to have a better understanding of how bonding happens, and that's the real reason for all of this extra depth in this presentation. So hopefully it doesn't turn your brain to mush. Hopefully you feel, I would say hopefully you feel encouraged by the fact that I'm presenting to you super duper hard information. And again, you'll come back with questions if you have them, and we'll talk about it. So moving on to our last segment, we're going to have our special presentation of bond length and strength. And you can do the drum roll if you want. I'll pause a second. Okay, good. Hope you did the drum roll. All right, so moving on. So bond length. Obviously, this is not animated. Wonderful. So question, which bond is the longest? Single, double, or triple? Answer, single. This is something that I know I talk about in general chemistry, so hopefully this will be something that you remember. I'm not sure if Mr. Wolf goes into discussions on bond length and strength, but I guess you can tell me later. So the reasoning. And I'm just going to read it directly to you, so just follow along. There is direct proportionality. More electrons shared between atoms, more need for atoms to stay connected together. It's an octet rule thing. So there's a direct proportionality between the number of electrons shared and the need of those electrons to stay connected to each other. So a single bond, which involves sharing only 2 electrons, doesn't pull 2 atoms together as close as a double bond would with 4 shared electrons. A triple bond, then, will pull atoms the closest together because they have 6 electrons being shared. So longest bond, single, shortest bond, triple. Cool. How about strength? So how are bond length and strength correlated? That's right. You guessed it. Longer bond, weaker bond, shorter bond, stronger bond. Another way I like to think about this is karate chopping boards, which I do in my off time all the time. A single bond is the longest, right? So think of a single piece of wood that you're going to karate chop through. Yeah, I'd definitely be able to karate chop through that board. Easy peasy, no problem. But the shortest bond, the triple bond, now that's 3 boards. That's strongest. Chances of me karate chopping through that is, yeah, that ain't going to happen. I'm going to break my hand. So if you think about it as karate chopping boards, the bond length and the bond strength, I think, really go together. Okay, so the last thing is talking about something called bond order. It is a fairly simple concept. You just have to know what bond order means. So in the blue, just read with me. A bond order of 1 correlates to a single bond. Okay, single bond, 1. Hence, 1 sigma bond. Oh, and this is the longest length. Okay, so a bond order of 1 is a single bond, and it's always a sigma bond. Okay, longest bond. A bond order of 2 correlates to a double bond, and that's 1 sigma and 1 pi bond, and it's a bit shorter than a first order bond, which would be a single bond. A bond order of 3 correlates to a triple bond. That's a sigma bond and 2 pi bonds, and it's the shortest bond length out there. Okay, so again, relatively simple concept, but notice how much stuff we're putting together right now. We're putting together sigma and pi, we're talking about length, we're talking about strength, and then this thing called bond order. So bond order, 1, single bond, 2, double bond, 3, triple bond. Okay, final slide. When you consider a molecule that has resonance, so do you see we have here NO3, nitrogen trioxide. We've talked before, right here, that we understand that we don't actually have two singles and a double. You do not say that you have two first order bonds and one second order bond, because if we recall, there are really no true single or double bonds, but instead all bonds are hybrids and have the same length. So hopefully we remember that we have delocalized bonding with resonance and that they are all an equivalent length. And this is something I alluded to before, which I hope you understand now. These bonds that you see in the nitrogen trioxide are shorter than a typical single, but they're a little longer than a typical double. And what we would call this is, let's say, a 1.5 bond order. It seems to be a good ballpark value, don't you think? You know, we don't really have true singles or true doubles, but something in the middle. So we call that a 1.5 bond order. So lots of stuff in this. Kind of a long video here, but I hope that you have gotten some good information, that you at least have some good questions. If you aren't understanding 100%, that you bring back your good questions, and then we can have some talks when we get back to class. So thanks for sticking with me. I know this one was a little bit rough, but awesome job.